All right. So I was getting coffee the other day and I was in a rush because I read the timetable wrong and I was going to be late for a class. And so it became a real concern to me how quickly they were making my coffee. And so I was wondering to myself, how long will it take to get my coffee? And yeah, it's deeply mathematical if we think about it. So let's jump into it and have a think. Imagine we wanted to work out sort of the amount of time it takes to get your coffee on average at sort of a specific cafe you go to. What we could do is we could have stood there and we could have, looked at all the customers and sort of measured how long it takes for them to get their coffee. Um, and then we can group it into bins. And you might have seen a histogram before. You sort of put it into like, maybe some people it's between 0 and 1 minute, and then some other people it's between 1 and 2. And then you could create a histogram of frequencies and you could collect all that data and you might get something like that. You'll notice on the left-hand side in this y-axis, we've got the density. Now, you're probably wondering what density is. Usually we're used to having like frequency along there. But I suppose what we could think about it is like, we can think about it in terms of how likely it is that you're going to get your coffee between, 3 and 3.5 minutes or 3 and 3.5 minutes type thing. And then what the really cool thing is you could basically put a smooth curve to that. And then you could create a function that sort of smooths out that histogram. And so then what you've created is you've essentially created what's called a probability density function. And I think that's a really important idea, really fascinating idea. And you don't need to know too much about, this function itself, but just be rest assured that, a curve that looks like this, I think it's called what's called a gamma function, has this type of equation. And so we might get something like this, and we sort of smooth our histogram out and make it into a nice function, and we get something like that. And then we get a probability density function, as we said, where the area underneath the curve represents the likelihood. Now, this is where it gets a bit tricky and gets a bit mathsy, but we're saying, all right, we're taking the area, and basically to find an area underneath the curve, you take the integral from some point A to some point B of that function. And so let's maybe look at what that looks like. So this pink area underneath here would represent the likelihood. So the area under here would be the likelihood that I get the coffee between 2 minutes and 5 minutes. And just really cautiously here, we need to be careful. Any point on the curve, f of x does not represent a probability, because the probability that we get the coffee at exactly, say, what's this, 3.5 minutes or 3 minutes and 30 seconds is actually 0, because no one gets it at exactly that time, because this is what's called a continuous random variable. Because, if you measure it really accurately, 3 minutes and 30 seconds and 42 milliseconds, it's a continuous variable, so it varies continuously. So the only meaning we can create out of this is by finding areas underneath this curve, which I think is interesting. And so, we've got to answer the question now, how long will it take to get my coffee? Well, one thing we could do is find out what's called the expected value, or the mean. So how do we find the average time it would take me to get my coffee? And so we want to find the average time. And then, so this part's the tricky part, but basically we weight each value by its density. So remember on that y-axis, we had our density. So we're saying, near the middle there, near that 3 minute mark, it was more likely that I was going to get the coffee there. So, the density is just how we sort of measure this, likelihood. So we add those contributions using an integral. And this is what the formula is. And, I hope that makes some sort of sense. We're taking the integral from the start to infinity off to the right. And we take, we weight each value by its density, So this x value represents the value. And then this f of x is the density at that point, or how likely it is that you're going to get your coffee at that point. Okay, and then, so if we apply that to this, now, as I said, this function is what's called a gamma function. Basically, you can set these parameters 3 and 1.2, but don't need to worry too much about that. Basically, you'll get this, and you're just computing this, and you're not at all expected to know how to calculate this, but this is sort of the big concept here. This is how you'd calculate the expected value of a continuous random variable. And so you'd end up with this. Again, you don't need to compute this by hand, but the expected value is 3.6 minutes. And so if we go back a little bit, so that answers the question, by the way, how long will it take to get my coffee? Well, on average, it's going to take 3.6 minutes. And, it doesn't look too bad. Over here, on average, we could expect, because there's quite a tail to the right, the average might get pulled towards the right. So yeah, that sounds about reasonable that we get our coffee in about 3.6 minutes. So hopefully that explains continuous random variable a little bit, sort of from the ground up. If you found that useful, give us a thumbs up. Good luck with all your studies, and hopefully your coffees come quickly in the future. Bye.